Hi, welcome to this video where we're going to be talking about rates of change. This is the 5th video on differentiation. I really like this topic. It really brings together the usefulness of calculus and seeing how things relate in simple physical situations and how we can use calculus to describe the relationship. It's a great topic, this rates of change, but some tricky problems. So I've got 3 problems here that we're going to look at. First of all, when we're talking about rates, as soon as the word rate is used, the rate something is happening, that word sometimes confuses people. It's just good to know that when we use that word, we're talking about with respect to time. So the rate, the radius is increasing, that's a derivative. That is dr dt. The rate, the radius is increasing. dA dt here is the rate that the area is increasing. So as soon as you hear the word rate, you know it's going to be dt at the bottom. We're talking about with respect to time. So let's look at this really simple situation here. Imagine a shock wave expanding in a circular shape. Okay, so we've got a blast at the center and a shock wave expanding in a circular shape in every direction. From that situation, you can get a sense that there's a relationship between the rate the radius is increasing and the rate the area of the shock wave is increasing. Okay, so as the radius is going faster and faster and getting bigger and bigger, certainly the area is getting bigger, but what's the relationship? Is it getting twice as big? Is it 4 times as big as the radius? We can use calculus to actually nail this and see what it actually is. So using the chain rule, let's look down here. dA dt, the rate that the area is increasing, is equal to the rate that the radius is increasing times question mark, question mark. Now you need to fill in these blanks. In these questions you've got to find out what these two are. If you remember that these things behave like fractions, you can fill these blanks in. So the way that I do this is I think, well, over on the left hand side I need a dA on the top. I don't have one on the top over here, so this one up here has got to be dA. Over on the left hand side we've got dt on the bottom, we've got dt here. We've got a dr on the top, so we're going to have to cancel the drs. So this bottom line here has got to be dr. So that's how I come up with this second fraction here, dA over dr. Now you can see that the drs cancel. We've got dA dt, dA dt. So this works. Alright, so the rate that the area is increasing is the rate the radius is increasing times dA dr. Now that's something else, dA dr, that we're going to have to work out. In this case, we're talking about a circular shock wave. So we've got a relationship between A and R. We know that that is pi r squared. So we know dA dr is 2 pi r. And we can put that in there. Let's look at this specific example with some numbers. We've got a radius, it's increasing at a rate of 100 meters per second. Okay, so the radius is growing at 100 meters per second. Really fast shock wave. Find the rate of increase of the area at the exact instant the radius is 200 meters. So if we put all the values in, dr dt, the rate the radius is increasing is 100. dA dr, we've worked out up here, dA dr is 2 pi r. And we want to know exactly what's happening when r is equal to 200. So we substitute in r equals 200, which gives us about 126,000 meters squared per second. Notice if we're talking about when the radius is 400 meters, it would be a lot quicker. The area would be increasing a lot more as the radius gets bigger. And if you think about that, that makes sense. If you've got a very small circle and the radius is increasing, the area is increasing at a small rate. But if you've got a really large circle, then the area is increasing a lot more at any given instant of time. So let's look at this example now. We've got an ice cube. So each of the sides is length L. It's melting, so the rate of decrease of the sides of the cube is 5 millimeters per minute. So straight away, start drawing a picture if you can. If it talks about a cube, draw a picture, give it a label. You could call it X, whatever you like. I've called it L. And straight away I know that the thing that we're given here is dL dt, the rate of change of the side length, and that is 5 millimeters per minute. Be careful with the units here, okay? 5 millimeters per minute. You've got to work in millimeters per minute for the whole thing. Find the rate of decrease of the surface area of the ice cube when the side length is 2 centimeters. Okay, so let's go through the steps. Let's write down what it is we're asked to find. We're asked to find the rate of decrease of the surface area, so I'm going to call that ds dt. I'm going to say the surface area of the cube is S, and we're asked to find ds dt. We're given dl dt, and we need to fill in this blank right here. So like I did before, we haven't got a ds on the top line, so I need a ds there. We've got no dl on the bottom line, just dt, so I need a dl on the bottom line. So I've got ds dl. Okay, so that gives me this bit down here. Now, what's a relationship between S and L? The surface area of the cube and the length of the side. We know that. The surface area of the cube, each side is got an area of L squared, and there's 6 sides of the cube. So the surface area is 6 lots of L squared. So doing the derivative now of this function, ds dl is 12L. Right. So let's substitute that in to this little equation here. We've got dl dt, we know that that's 5 millimeters per minute. We've just worked out ds dl is 12L. So now we want to know what's the rate of change of the surface area at the exact instant when L is 2 centimeters. Now just be real careful here, because remember this is in 5 millimeters per minute, so we should be substituting L in millimeters here. Okay, so 2 centimeters is 20 millimeters, so that's an important thing that you've got to watch out for here. So multiplying these out, we get 1200 millimeters squared per minute. Notice the units, because we're talking about surface area, the units are millimeters squared per minute. I mean, you could change that if you wanted to centimeters squared per minute. You'd have to just divide by 10 twice, so it'd be 12 centimeters squared per minute if you want to, but I'd advise you just to stay in the original units of the problem. Okay, this problem's a little bit different. I'd never seen one like this until I saw one similar to this in the exam. We've got the equation of a curve and a point moving along the curve in such a way that the rate of increase of x has a constant value 0.02 units per second. Find the rate of increase of y at the instant when x equals 4. Okay, this is a strange kind of problem. So we want to find, let's identify what we want to find. Find the rate of increase of y. As soon as it says rate, you know you're talking about dt with respect to time. So the rate of increase of y is dy dt. That's what we were trying to find. The thing that we're given is dx dt. The point moves along the curve in such a way as the rate of increase of x. So this is dx dt, and that has a constant value 0.02. So we know dx dt is 0.02. Okay, so using the chain rule, dy dt, that's what we're looking for, is equal to dx dt, that's what we're given, times by, this is the bit you need to come up with, and it's dy dx. You can see that the dx is cancelled, get dy dt, beauty. dy dx is what we're after, and luckily we've got the function y in terms of x. So dy dx is just a matter of doing the derivative, which I've done up here. It's using the chain rule. So number down the front, subtract 1 from the power, multiplied by the derivative of what's inside here, which is 6, and then just tidy it up. 6 on the top, 2 on the bottom cancels to give you 3. 1 plus 6x to the minus a half is 1 plus 6x to the plus half on the bottom. So this is dy dx. So here we go. dy dt then is dx dt, which is 0.02, times dy dx, which is this thing here. And we want to know exactly what's going on when x is equal to 4. So then I substitute 4 into this. It actually gives me a nice number on the bottom here. 1 plus 24 is 25, root 25 is 5. So 0.02 times 3/5 is 0.012 units per second. Once again, just be careful with the units here. The rate of change of x was units per second, so the rate of change of y is units per second. There's a number of really good problems in the workbook that I like on this topic. We've got tanks being filled with water. Obviously the rate of change here, if the water's going in constantly, the rate of change is going to be constant. So it doesn't matter how high the water is, it's always going to be rising at a constant rate in this case. Number 4 is a very common one where we've got a balloon being blown up, and you've got a number of things related here. As the balloon's being blown up, the radius is increasing, the surface area is increasing, and the volume is increasing. So all of those are related. Number 4 is a really good problem to see how those rates all relate to each other. Number 5 is dedicated to my mum, who took me to the races a lot when I was a young boy. So we've got a horse racing around a track, and we're looking at the rate of change of this angle here as the horse races around the track. I've seen other problems like this where a balloon is going up in the air and you've got a camera following the balloon, and what's the rate of change of the angle of the camera as the balloon rises. So these are very applicable kind of problems. Number 6 is kind of the hardest ones that you'll get in the exam, where you've got a irregularly shaped object. And you can see, because of the shape here, as you fill this water trough up with a tap that's going in at a constant volume, it's going to start off quickly, but because of the shape, as you get further and further up, the rate of change of the height slows down. So this is a tricky problem, number 6.